Hi everyone, welcome back to Chemistry Portal. I am Sudhanshu Kumar and today in this lecture we will talk about orbital angular momentum. So the first thing we have to know that is angular momentum, right? In both the cases, classical mechanics and quantum mechanics. In the classical mechanics, first we will discuss one by one. First we will go classical mechanics. In the classical mechanics, suppose we have example like Earth of mass m, it is revolving around the sun. Okay, here at this point you have here sun, right, and around the sun the Earth is revolving in this plane. Okay, and perpendicular to this plane we have L vector, and this L is what? This L is your angular momentum, right? And this P is your linear momentum. Okay, right? So angular momentum, it is a vector quantity, and vector quantities have both magnitude and directions also, right or not? Okay, fine. Now, and angular momentum, it is defined in the classical mechanics is L vector equal to R vector cross P vector, right? So this is a angular momentum, and note here angular momentum has direction that is perpendicular to the plane of motion of the earth around the sun. Suppose this is your mass m of earth and it is revolving around the sun in this plane. Okay, so the angular momentum vector direction will be just perpendicular to this plane. Okay, perpendicular to this plane, right? Okay, now the magnitude of the angular momentum is not restricted by the nature of the system. Okay, the magnitude of the angular momentum in the classical mechanics, it can take any value. It is a continuous value. Okay, magnitude is continuous value, not quantized. Okay, it's not a discrete value. It can take any value. It is a continuous. It can take any values, right? So these all things are in the classical mechanics. Now one more thing, angular momentum, or we can say momenta, can point in any direction in a 3D space depending upon if there is a planet which is revolving in that particular plane. See here, this angular momentum, right? This angular momentum direction, this L vector, it can point in any direction, any direction. Understood? It is not restricted. Okay, angular momentum can point, can take, can point in any direction in 3D space. Okay, this is all the things in the quantum, sorry, in the classical mechanics, in the classical physics. Okay, right? And there is no restriction in direction, means it can take any direction in the space. Okay, right? Now angular momentum direction is not quantized. Okay, it means not quantized means it is not it is not fixed. Okay, it can take any direction, it can point in the any direction in the 3D space. Now we will talk about angular momentum in the quantum mechanics. Okay, so in the quantum mechanics, suppose we have electron. Electron is revolving around the nucleus and that produces angular momentum. Similarly, like Earth. Earth revolving around the sun and produces angular momentum. Similarly, in the quantum mechanics, electron is revolving around the nucleus and that produces angular momentum, and that is called orbital angular momentum. Right? Now, but there is a very interesting things in the quantum mechanics, the magnitude and the directions of angular momentum of electron is quantized. Okay, quantized. Quantized means it is some restricted value. Okay, restricted value or some fixed value. Fixed value. Okay, understood. in the classical mechanics, angular momentum direction, it can take in any direction, can point in any direction in the classical mechanics, and the magnitude also, it can take any values. It is the magnitude of the angular momentum in the classical mechanics, it is continuous value, not quantized. But in the quantum mechanics, the magnitude and direction of angular momentum of electron is quantized. And why it is quantized? Due to quantum number. Okay, quantum number put restrictions on magnitude and direction of angular momentum of electron. Understood? Right, because in the quantum mechanics we have quantum number, right, and that quantum number governed that quantum number governed the orbital angular momentum, and due to this, quantum number put restrictions on magnitude and direction of angular momentum of electron. So the conclusion is like angular momentum in the quantum mechanics, it is quantized, it is fixed, magnitude also fixed, directions also fixed, but in the classical mechanics it is not fixed. Angular momentum, it is not fixed, the magnitude, it can take any value, it is a continuous value, and angular momentum in the classical mechanics, it can point in any direction. Okay, so this is a major difference of angular momentum in the classical physics and in the quantum mechanics. Now, so this is a diagram. We were having electron is revolving around in this plane, right, and around this plane to the perpendicular you have a L vector, that is a overall vector, right, L vector of this angular momentum produced due to electron is revolving around this plane. Okay, right, and this L vector has some components in all the directions like Ly, Lx and Lz, right. Sorry. Now, in the quantum mechanics, the magnitude of the orbital angular momentum, it is given by under root of L into L plus 1 into h cut over h cross. Okay, understood? This is very, very important. Okay, in the quantum mechanics, the magnitude of the angular momentum overall, it is equal to under root of L into L plus 1 into h cut. Okay, this h cut is outside of the root. Okay, right, and where L is what? L is Azimuthal quantum number, and this L value can take value from 0 to n minus 1, but only integral value, right? And due to this L value, the magnitude of the orbital angular momentum, it is quantized because L value can only be integer, right? So that's why due to this L value, the magnitude of the orbital angular momentum, it is fixed, it is quantized, it can take only fixed value, right or not? Okay, now so there is some points in the classical mechanics we have left it here. There is no, okay, these all things done, right? Okay, so in the quantum mechanics, the magnitude of angular momentum, it is given by under root of L into L plus 1 h cut. Okay, and this h cross equal to what? H by 2 pi. Okay, this h cross equal to h by 2 pi, right? Now if suppose electron is present in the s orbital, and if you want to find the orbital angular momentum of that electron that is present in the s orbital, that is revolving, that is doing a motion, and due to motion we got orbital angular momentum. So for the s orbital we have L value equal to 0. So if you put the value here 0, you will get L equal to 0. So there is 0. The magnitude of orbital angular momentum in the s orbital is 0. Always it is fixed. Okay, understood. If any electron will be present in the s orbital, their angular momentum magnitude will be 0. Simple, right? Now, for suppose if electron is revolving, doing a motion in the p orbital, and for the p orbital the L value is 1, so if you find the magnitude of angular momentum, you will get here under root of 2 h cut. Why? So if you put the value here L equal to 1, so 1 into 1 plus 1 into h cut, you will get here under root of 2 h cut. Okay, this is called h cut, or you can say h cross. Okay, both are same. Okay, right. Similarly, for the d orbital, we can also find the orbital angular momentum if electron is present in the d orbital, and due to the motion of electron in that plane, it can generate orbital angular momentum, and that will be equal to, and we know that for d orbital L equal to 2, so if you put the value here, you will get here under root of 6 h cut, right, or h cross, under root of 6 h cross, right. Now, these things may be new to you and maybe something confusing to you, but don't confuse, okay. These all things came from quantum mechanics, right, commutator and all, but we will not go in deep in the commutator and all the things, right, because this is a course of introduction to organic chemistry, right. So we will just overview of orbital angular momentum, right. We will talk in more details about this commutator and all things in the quantum mechanics separate video, okay, right. So very important here point is Lx, Ly, Lz cannot be determined simultaneously, okay. It means at the same time you cannot find the value of Lz, you cannot find the value of Lx, you cannot find the value of Ly. Very important, okay. And the reason is commutator, okay, because all these operators they do not commute, okay, understood. So that's why we cannot find the value of Lx, Ly and Lz at the same time, and cannot be determined simultaneously, okay. For now you can just remember, okay, the reason will become in the quantum mechanics in more detail, understood. But remember this thing, Lx, Ly, Lz we cannot determine simultaneously, okay. But magnitude of L, magnitude of angular momentum and Lz component we can determine at the same time, okay. Similarly, magnitude of angular momentum and the component of Lx means the component of orbital angular momentum in the x direction we can determine simultaneously. Similarly, magnitude of L vector and Ly can be determined simultaneously, okay, right. And from the quantum mechanics, this is result given Lz, the magnitude of angular momentum in the z direction, that is called Lz, equal to ml h cut, okay, or h cross, okay, understood. This is very important. The magnitude of orbital angular momentum in the z direction, that is called Lz, and this is given by this is given here, this is equal to ml means magnetic quantum number, okay, magnetic quantum number, ml into h cut, okay, and this value is quantized. It means Lz is what? Quantized. Whole orbital angular momentum is quantized, right or not? We already talked about this, right? In the classical mechanics, angular momentum is not quantized. In the quantum mechanics, angular momentum is quantized. Understood? This is a major difference between in the classical physics and quantum mechanics. Okay. So this is your z component of orbital angular momentum in the z direction, and that is equal to ml h cut. Right. Now, so why we are talking about only Lz? Why not Lx? Why not Ly? Why not L? So why we are talking only about LZ and why we have chosen LZ. So basically, it is a natural choice, okay, now because gravity, magnets, and many forces align with the vertical direction. Understood? And that's why Z direction is the natural choice. Okay, understood? Other directions, suppose if you find the Lx or Ly, then that would make the math more and more complex and more harder. Okay, we can find, but that will be more complex and the math becomes more complicated. Understood? So that's why the reason to choose LZ, Z direction is why, because it is a natural choice because gravity, magnets, and many forces align with the vertical direction, and that vertical direction is naturally it is taken as a Z axis. Okay, understood? So that's why this is very very important. The magnitude of angular momentum of orbital angular momentum magnitude in the Z direction, that is called LZ, and LZ equal to ml h cut. Right? It means LZ can have many value because if you put the ml value, the LZ value will change. Right or not? So suppose for p orbital we know that ml value is how much? -1, 0, +1. Right? We have already discussed the Azimuthal quantum number, principal quantum number, magnetic quantum number. You can check the playlist. All the links are given in the description box. Go and check it and see the videos from starting. Okay, understood? Now, so we know that for the p orbital, the possible ml value equal to -1, 0, +1. So if you put the value here one by one, so you will get three different value of LZ. Right or not? So -1 into h cut will get here -1 h cut and 0 h cut and +1 h cross. Right or not? So LZ value having a 3 magnitude on the Z axis. 3 value you will get. First of all, -h cut, 0 h cut and simple h cut or h cross. Similarly, we can find for the s orbital, and we know that for the s orbital, L value is 0, right? So, and for the L value 0, ml value also 0, so this 0 value will put here, you will get LZ equal to 0. It means there is no magnitude for the s orbital electron on the z axis, on the z component. Okay, that's why LZ equal to 0. Why? Because from this equation, if you put the value here ml, you will get 0. Okay, right? So how the electrons are oriented, how the L vector is generated. Now I will give you feel in the 3D. Okay, see here. See, all this value came here, right? For LZ we got the value 3 value we got for LZ for the p orbital, and here we got 1 value, that is a 0 for the s orbital. So what does this mean? What does this 3 value mean? See, what happened? So first of all, if you have ml equal to +1, right? So okay, wait. Note, the electron orient itself in such a manner so that z component of its angular momentum with respect to that z axis will only have these 3 value. Okay, to get this value, to get this components on the z axis -h cross 0 and h cross, the electron will orient itself in such a manner so that z component of the angular momentum will give this 3 value. Okay, now let's take some more feel of this thing, how it is happening. See here. For suppose ml equal to +1, okay, and these all things we are discussing for the p orbital. Okay, if electron will revolve in this plane, okay, try to fill in 3D. Okay, if electron will move in this plane, then we know that angular momentum will be generated in the perpendicular of this plane. So for this plane, the perpendicular direction is what? This direction. So this is your overall L vector. And now we have to take the component of this L vector on the z axis. So if you take the component of this L vector on the z axis, and because this is a straight line, it is our z axis, so you will get some value here, and that is your h cross. Understood? So for the ml equal to plus 1, see here, for the ml equal to plus 1, so this value becomes h cross. It means it's a positive value, right? So this value, this point, it is your h cross, right? Similarly, for the ml value equal to 0, and we know that for the ml equal to 0, we got here Lz equal to 0, right? 0 h cross, 0 h cut, right? So it means for the ml equal to 0, the magnitude of components on the z axis is 0. It means if electrons will do a motion around this plane, and we know that the plane to this perpendicular direction is this one, and this is your L vector, and we know that here L vector having no components on the z axis, and that is why it is 0. Understood? So for the ml equal to plus 1, the Lz equal to what? H cross, and for the ml equal to 0, the magnitude of this L vector on the z axis, it is 0. Right? It means now if electron will move in this plane, then and only the angular momentum vector will oriented in this side, perpendicular to this plane, right? Perpendicular to this plane, the angular momentum vector, this is the projection of angular momentum vector, right? And if you want to find the magnitude of this on the z axis, on the z component, so here just extend the line and find this value. So this value will come h cross, but minus h cross, okay, minus sign here, right? Because for the ml value equal to minus 1, we got here minus h cross, right or not? If you put the minus 1 here, you will get here Lz equal to minus 1 h cross, that is a minus h cross, and that's why this value, this is your z axis, and this is your 0, and here all the value are positive, here we have all the value are negative, right? So that's why this component for the ml equal to minus 1, the component of Lz on the z axis, it is a minus h cross, right? Similarly, we can find for the d orbital, and we know that for the d orbital we have Lz equal to ml h cross. See, Lz equal to ml h cross, this is valid for all the orbitals, okay? Either it is s, p, d, f, any orbital, the z component will be same, that is the ml h cross, okay? And we know that for the d orbital we have ml values, we have 5 value, right? Minus 2, minus 1, 0, plus 1, plus 2, right? And if you put the value here one by one, then you will get here 5 components, 5 value on the z components, okay? On the z axis you will get 5 value, that is a minus 2 h cut, that is a minus h cut, 0, and plus h cut, and 2 h cut, okay? And to get this value, electron will orient itself such that so that you will get this component on the z axis. Understood? So if electron do a motion around this plane, then about this plane, this is your perpendicular direction, and that's why here angle is a 90 degree, and for the ml equal to plus 2, we will get here Lz equal to plus 2 h cut, okay? And similarly we can find for the ml equal to 0, right? So for this ml value 0, it means if electron will revolve around this plane, then this L vector will oriented in this direction. And because this is your L vector, and because on the Z component we have a 0 value of Lz. Okay, so for the Lz and for the ml equal to 0 we have 0 value here, right? And if electron will revolve around this plane, then the angular momentum vector will come this side, and if you take the components on the z axis, we'll got here minus h cut, right? And similarly for the ml value plus 1, if electron will revolve around this plane, then this angular momentum vector will project in this direction, right? Perpendicular to this plane, right? And if you take the component of this L vector on the z axis, we got here plus h cut, right? Similarly, so here for ml equal to minus 2, so if electron will move in this plane, then and only this vector will project in this direction. And now if you take the component of this z axis, of this vector on the z axis, you will get here minus 2 h cut value. That is the magnitude of Lz, okay, in the case of ml value minus 2, right? So this figure shows that like around on the z axis you have different magnitude of Lz, right? See here 1, 2, 3, 4, 5, and from here also we got the 5 value. See here, and this all value here plus 2 h cross, here plus 1 h cut, here 0 h cut, here minus 1 h cut, and here minus 2 h cut. And these are the directions of the angular momentum vector overall. Okay, these are the L vector, right? That is oriented in the 3D space. Okay, and this diagram you are seeing here, this is called vector model. Okay, this is called vector model. Basically, all the cones here, all the cones, these are the cones, understood? So all these cones like represents the magnitude. All the cones here represents the magnitude of the orbital angular momentum on the z axis, right? So this is a minus 2 h cut, this is a plus 1 h cut, 0 h cut, minus 1 h cut, minus 2 h cut, right? And each and every cone has a different projection of ml units on the z axis, right? Understood? All the cones having a z axis, having a projection on the z axis. So if you see for this cone, this is having here minus 2 h, plus 2 h cross, and for this cone we having a projection on the z axis. We have this value is plus 1 h cut, and for this cone it is a 0 here, and for this cone we have a projection of this ml value we got here minus 1 h cut, and for this cone we have this projection, this distance on Lz, that is a minus 2 h cut, right? So this is called vector model, right? Okay, and these are the permitted orientations of angular momentum when the L equal to 2. It means when you have d orbital, then it means electron has to revolve in this and only plane, so that you will get all these 5 value, right? So these are the fixed plane. Okay, if electron will move in this plane, then and only you will get here Lz value equal to plus 2 h cross, plus 2 h cut, right? And similarly all these are the orientations, right? Okay, so this is all about orbital angular momentum. Okay, I know that this is a little bit complex, all this diagram, but if you have good knowledge of vector and quantum mechanics, you will understand easily. Okay, but for you, for the introduction of organic chemistry, up to here only sufficient. Okay, no need of to see the cones and all. Okay, right? And I hope you find this video helpful, and if you find this video helpful, so please like, share and subscribe our chemistry portal, and thank you everyone, thank you so much.